Hello everyone, welcome to Science in a Cup. Today we are going to know about spectrometer. So spectrometer is an amazing instrument that actually analyzes colors or wavelengths of light that are coming from an object. By analyzing these colors or wavelengths of light, we can actually tell the properties of the object from where the light is coming from. Properties like what are the chemicals bound in it, what are the ions it is made up of, or the elements, and various other properties of the object that can be analyzed through the light that is coming from that object. Each object in the universe, like stars or living bodies or tissues, chemicals, proteins, either absorb or reflect or transmit certain type of colors. By analyzing these colors or wavelengths of light, we can tell what type of molecules, chemical bonds, compounds, elements are present. This is a picture of a complete spectrometer. Our light enters through the narrow gap, then the diverging beam of light is collimated or made parallel, and it falls onto the diffraction grating, which is an optical element that breaks the light into its component wavelength. This is also called phenomenon of dispersion. After dispersion, the spectral component is imaged by our light detector and the signals are seen in a computer. So let us now see what are the different parts of a spectrometer in a very detailed version. The narrow aperture or entrance through which the light enters is called the slit. This slit is critical to the spectrometer's performance and determines the amount of light that enters the spectrometer or light throughput, and also determines the spectral resolution or how small the change in wavelength the spectrometer can detect. Light entering the spectrometer via a fiber or lens is focused onto the pre-mounted and aligned slit. The slit also controls the angle of the light which enters the spectrometer. Slit widths come in a number of different sizes from 5 micron to as large as 800 micron depending on the wavelength you are using. The height of the slit may be 1 mm standard to 2 mm height. The most common slits used in spectrometers are 10 micron, 25, 50, 100 and 200 micron, etc. In short, the slit width is one of the factors that affect the resolution and how much light is entering, and also the range of the spectrometer. Diffraction grating of a spectrometer determines the wavelength range and partially determines the optical resolution that the spectrometer will achieve. Choosing the correct grating is a key factor in optimizing your spectrometer for the best spectral results in your application. Grating will influence your optical resolution and maximum efficiency for a specific wavelength range. Now, the grating can be described in two parts: the groove frequency and the blaze angle. The diffraction grating itself is also of two kinds. One is ruled gratings and another is holographic gratings. Ruled gratings are created by etching a large number of parallel grooves onto a surface of a substrate and then coating it with a highly reflective material. Holographic gratings, on the other hand, are created by interfering two beams of light to create a sinusoidal index of refraction variation in a piece of optical glass. This process results in much more uniform spectral response but a much lower overall efficiency. While ruled gratings are the simplest and least expensive grating to manufacture, they exhibit much more stray light. This is due to surface imperfection and other errors in the groove period. Thus, for spectroscopy applications such as UV spectroscopy, where the detector responses is poor and the optics are suffering more loss, holographic gratings are generally selected to improve the stray light performance of the spectrometer. Another advantage of holographic grating is that they are easily formed on concave surfaces, allowing them to perform as both dispersive element and focusing optic at the same time. In modern spectrometers, CCD and linear detectors is actually useful for development of fixed grating spectrometers. As the incident light strikes the individual pixels across the CCD, each pixel represents a portion of the spectrum that the electronics can then translate and display with a given intensity using software. This advancement has allowed for spectrometers to be constructed without the need for any moving parts, and therefore greatly reduce the size and power consumption. Multi-element detectors are readily available in three different subcategories like charge-coupled devices, back-thinned charge-coupled devices, and photodiode arrays. Now, the gate structure on front of the CCD can cause incident light to scatter and therefore not to be absorbed. Photodiode array detectors are more traditional linear detectors which consist of a set of individual photodiodes that are arranged in a linear fashion using CMOS technology. These detectors, while not having the small pixel size and high sensitivity, have several advantages over CCD and BTCCD detectors. First, the lack of charge transfer eliminates the need for a gate structure on front of surface of the detector and hence greatly increases the readout speed. Moreover, their sensitivity is also high than CCD and BTCCD.
So that is all for today. Spectrometers are great instrument, great tool to understand the nature and the whole world around us, all its atoms, molecules and everything. So in the next video we'll discuss about the different configuration of a spectrometer. Till then, bye, and if you like the video, do subscribe to Science in Agla. Thank you. Bye bye.